Well, welcoming Catherine Yan, who will speak about U parking functions and PQ parking functions.
Thank you. So first, I want to thank the organizers, especially Tufik, for putting together such a wonderful program. And it's really an honor to speak here. So I'm talking about my favorite subject on parking functions. And here's my plan. So first, I'll recall the classical definition and some generalizations. What I want to propose today is a two-dimensional vector generalization of parking functions. I would say what's the definition, where the motivation comes from, and followed by some enumerative result. So first, the classical parking function. So for a sequence of n integers, let inc to be the non-decreasing rearrangement of the terms. It's also called order statistics. In my talk, my integers index from 0 up to n minus 1, and the values for my parking function can assume value 0 instead of in other literature, people taking positive integers, but that's just a little bit of rescale. So definition, an integer sequence of less than minus 1 is a parking function if and only if the ith order statistic is lying between 0, but at most I. So I give a bunch of easy examples as you can check. Among parking functions, there's a notion of increasing parking functions, which just means it is a parking function and the terms are already show up from small to large. And as we all know that the number of parking functions of length n is given by the Cayley's formula, n plus 1 to the power n minus 1, while increasing parking functions are given by the Catalan number. So I just want to kind of show you an easy picture to see why Catalan number shows up here. So here, taking an example, 0013 is a parking function of length 4. Well, we can represent this by a lattice path where you do put a horizontal steps at the height 0013 consecutively, and then connecting those red edges by some vertical edges. So it's a lattice path from the origin to the point nn, in this case 4. And what you can see is the original sequence is a parking function if and only if there's a lattice path lying sub-diagonal. So that's hence given by the Catalan number. Well, there are many different generalizations of parking functions. I think the most straightforward one, the natural one, is called a vector parking function. So which depending on some parameter, which I call U, which is to be given as a sequence of non-decreasing positive integers. And so if one want to define U parking function of length n, then you only need n terms from U. So the U parking function would be a sequence of non-negative integers so that the ith order statistic is lying between 0 and strictly less than UI. So the classical case corresponding to exactly U is 1, 2, 3, etc. And I also give another example, say U is 2, 5, whatever number following, and the U parking functions of length 2 will including this 9 sequences which are monotone and their permutations. So there are 9 increasing U parking functions and 16 U parking functions in this case. Well, the notion of U parking vector parking function was first proposed by Peterman and Stanley in a paper in 2002, where they easily result is this number of U parking function is a polynomial of the variables U0 up to UN minus 1. Well, Stanley's notation is a little bit different from mine because he used a vector, which is basically the difference of my U vector, but the results are equivalent. It's also give a this number is also given the formula volume of a special polytope called parking polytope, and it can be computed by a formula of stack from statistics. Shortly later, Joseph Cole and I found out that this polynomial actually can be related to something called a Gankarov polynomial, which is a solution coming from the Gankarov interpolating problems in numerical analysis. And this UI, U0, U1, etc., would be the interpolating points in the problem. So I don't want to go too deep into that line. It's just saying there is some polynomial coming from numerical analysis corresponding to the number of vector parking functions. And a similar result holds for increasing vector parking functions. When I say similar, that means first, the number of increasing U parking functions is also a polynomial depending on the U0, U1 up to UN minus 1. And there is a stack formula, which is in terms of a determinant to compute this value. And secondly, you can have another notion of Gankarov polynomial, which give you the formula for the increasing one. And the difference is just in the usual interpolation problem, we use the derivative. And in the increasing U parking function, we want to use the backward difference operator to do the interpolation. So I'm kind of for a long time interested in what's the natural higher dimensional generalization of parking function. And here there is one in literature defined by Corey and Polahon. In their paper, they have several equivalent characterizations, and I'm choosing this one because I think this is the easiest one to understand. So double PQ parking function would referring to a pair of integer sequences, one of length p and the other of length q. So when do you define a parking function? In this case, they described by such a parking kind of description. So you assume there are P red cars and Q blue cars. They want to park on a street with P plus Q spots. And the condition is for each driver I of a red car. The driver wants to have at least AI blue cars parked before him. And vice versa, each driver J of a blue car want to have at least BJ red cars in front of him. So if you can find a parking configuration that accommodates all the requirements, then the sequence is called a parking function. So I put a small example, which is a 4-6 parking function, and given by this a sequence of length 4, then followed by a sequence of length 6. And here is a parking configuration for 10 cars with 4 red and 6 blue. So if for the red car, you check how many blue cars are in front of them, then the number is 1 by 1, at least 0, 1, 2, 4. Similarly, you check for each blue car how many red cars are in front of them, and the numbers are at least 0, 1, 1, 3, 4, 4. So that gives this pair is a 4-6 parking function. So it's maybe a question where does this definition comes from? So Corey and Polahon proved that such a parking function is actually due to something called recurrent configuration of the center pile model on KPQ1, where KPQ1 is a complete bipartite graph on P and Q vertices together, in addition, having a root which connecting to all the vertices. So there's a natural generalization for the classical case because the classical case corresponds to recurrent configuration of the center pile model on complete graphs on n+1 vertices. And the major result in Corey's and Polahon's paper is they give the number of formulas for increasing parking functions and PQ parking functions. The increasing one is given by the Narayana number, while the number PQ parking function is given by this formula. So the major part is kind of like a power, similar like the one you have seen in the classical case, and with the additional factor. So this is what happens in the literature, and what I want to do is kind of looking for a definition in two-dimensional, but also allow a vector form in it. So for two-dimensional, we kind of can follow Corey and Palahan's idea. So it's referring to a pair of integer sequences. What replace the vector in the classical case would be a set of weight defined on the rectangle grid of size p times q. So what we mean is you look at a rectangle grid, and for on each edge, there will be an integer, not integer, but a weight defined on this. So in my notation, if I have a vertex ij, then the horizontal edges coming from there, as well as the vertical edge kind of growing from there, they are indexed by uij and vij. And just for simplicity, assume those numbers are non-decreasing. So you look at this weight. When you go to the right or go to the top, the weight are kind of weakly increasing. So the most important concept we have is something called the pair of integers is bounded by the lattice, bounded by a lattice path from origin to PQ with respect to the weight U. So what do we mean here? We're given a pair of integer sequences. First, consider their order statistic. So arrange both sequences from small to large. Then we want to compare these terms with the lattice path, and hopefully the terms are kind of alternatingly less than the weight show up on the steps of this lattice path. So I think instead taking the definition, I'll show you by an example. So here is a grid with a weight on all the steps, and the given integer pair, the A sequence is 232, and the B sequence is 3010. So what I'm going to do is put the order statistics or the increasing rearrangement of A on the bottom and the B on the side, on the left side. What I'm seeking up is integer lattice path from the left end to the right top. So for example, this right one I put here. And when you travel along this lattice path, for each vertical step, you want to compare the weight with the number on the left, which is B sequence. And for any horizontal step, compare the integer sequence on the bottom, which is the given by the A sequence. And if in all cases, the weight on the lattice path is bigger than what happens on the side, then we say this pair of integer sequences is bounded by this lattice path. Here is another example, a different lattice path, but if you travel along it, you can see that the weight is also satisfied in the same condition. The weight on the path is always bigger than what happens show up in the left or on the bottom. Actually, you can check in this picture, that's the only two lattice paths that can satisfy this condition. If you change to other lattice paths, this property will fail. But this doesn't matter how many lattice paths you can find. What we are concerned about is for the integer sequence, can you find such a lattice path or not? And here comes the definition. So we'll say the pair of integer sequences, A and B, is a two-dimensional U-parking function where you're referring to the weight. If and only if this pair is bounded by some lattice path from 0 to PQ with respect to the weight U. In the special case that the terms of A and B are already in non-decreasing order, then we call such a pair increasing U-parking functions. So I think natural question is, why do you think about this definition? Well, this definition comes from our study on the multivariate Gankarov polynomials. So this is actually true in general k-dimensional space, but let's just concentrate on what happened on two-dimensional. So there is a multivariate Gankarov interpolation problem, which in 2 dimensions means you want to find a polynomial in the variables x and y with a given bound degree, so that when you take partial derivatives to this polynomial, then evaluate at some integer, make some point, interpolation point, you get a desired value. Such interpolation problem always have a solution, and the basis of solution is called the multivariate Gankarov polynomials. Where the weight I have defined in previous pages actually offer you the interpolation grade. So each pair of weight gave you a point. That's your point to do the interpolation. In the Gankarov polynomial problem, if you use the partial derivative, we got the solution. That is the polynomial corresponding to the U parking functions. And if we change the differential operator to partial backward difference operator, then the polynomial we obtained corresponding to the increasing U parking functions. So back to Corey and Polahan's definition of PQ parking functions, then it's interestingly, their notion is a kind of a special case of our, I think it's not surprising, but PQ parking function is a special case of our 2-dimensional vector parking function. And actually, in some sense, it's the first non-trivial case because the weight is kind of given by a twist of the coordinate I and j. There are some people familiar with parking function. There's a notion of G parking functions defined on NA, I think actually direct graph with a think. I have to point out that the 2-dimensional U parking function and the graphical parking function only have a very small overlap. It's in very small cases, you can realize both. In general, so to study this 2-dimensional vector parking function, we can use a theory about multivariate Gankarov polynomials. There are some analytical formulas available. However, if you want to say found an explicit formula for the number of such parking functions, it is kind of hard because what we have is a general determinant formula that's hard to evaluate. Nevertheless, there is a special case where there are certain nice analogs of some value like this, kind of look like Abel polynomials and the fused Catalan number. People familiar with the parking function will realize these numbers are given give you in the 1-dimensional case number of vector parking functions and the increasing ones when the vector is arithmetic progression. So in higher dimensions, we have some analog of this arithmetic progression, which we call this a fun case. That's the cases where the weight Uij, Vij is actually given by a linear transformation of the coordinate point, where here the entries of the matrix are all just the non-negative integers. So with some help from the analytic result on the Gankarov polynomial, we can obtain the exact formula for the number of increasing parking functions and increasing and just general U parking function in 2 dimensions. And the formula is kind of have a nice factor. It's a product of small terms. For the U parking function, the major term would be this 2 power and with a particular quadratic term. And in the increasing one, other than this scaling factor, the major terms is this polynomial, which is representing the rising factorial. So you can easily check when you go back to the special case for the PQ parking function, we do realize the Narayana number and the easy power showed up by Corey and Polahan. So here is some interesting observation. Look at this ratio. Nth scalar number over 2 and choose n equals to this ratio, which is equal to 1 over n plus 1. What does it say? Well, it says in the classical parking function, consider all the integer sequences of length n, where each term is coming from 0 to n. Then the ratio of the increasing parking functions over all the increasing sequences in this range is the same as the ratio of all the classical parking functions over all possible sequence. Same result is also observed for PQ parking functions. But with what we have, with the formulas we have, we kind of got that such a result holds for all affine cases. So you take the affine weight, then for the integer sequences A and B, thinking of all the pairs where A is a sequence of length P, and the terms are coming from 0 with this value. And the B is defined similarly. This final value is the maximum value allowed by the weight. Then we can prove that for all the such weight, and the portion of increasing vector parking functions over a pair of increasing sequences in this range is the same as the ratio of the forget about increasing all the parking functions over all possible sequences. And this one is actually even true for integer, for all dimension. So in the remaining time, I kind of want to concentrate back to the PQ parking functions of Corey and Polahim, but I'm going to look at the increasing ones and see what's our new interpretation of using the grid and the lattice path can say about such parking functions. So because in that case, the weight is so special, you can actually view those parking functions from a different point of view in terms of lattice path. Let me explain how. So here is my grid, and I forgot about the weight, and that's the two sequences, increasing sequences. What I will do is kind of for the bottom one, 2 to 3, I just write the horizontal steps of height 2 to 3. Now connecting them by the vertical steps, so it is a lattice path from the left lower corner to the upper right. I'll do the similar thing for the right sequence 0, 0, 3, 1. So these numbers will be represented by vertical steps, which have the x coordinate 0, 0, 1, 3. Then I connect them by the horizontal steps to make this a lattice path. So what you can see is such a pair. You will already know this pair are parking functions in the two-dimensional case, and the picture kind of shows there is a sense of non-crossing lattice path appeared here. And this is actually the correct description. So we have an increasing pair of integers of length PQ is a PQ parking function if and if only if the corresponding lattice paths are non-crossing. Here, when we say non-crossing, we do allow they share some common edges. Just in the previous picture, the blue one cannot go down below the orange one. With this notion of non-crossing lattice path, then we can use knowledge of the lattice path to compute how many are there, and not surprisingly, the Narayana number shows up. Well, actually, we can do a little bit more. So instead of just looking at how many are there, let's consider the bivariate generating function for those increasing PQ parking functions. So I'm summing over the PQ parking function where the enumerator is at the same time, I want to count the total sum of AI and the total sum of the BI sequences. From the previous picture of two lattice paths in a rectangle grid, it's quick to see such a enumerator that is symmetric. Either you change the index or you change the two variables. And the boundary condition was given by the Gaussian coefficients because they're just counting lattice passes by its weight. Well, my original purpose to study this is kind of I want to see whether that will give me some kind of a different refinement of the QT Catalan number. Well, that doesn't happen. It is not same as the data, but nevertheless, we do obtain something very neat about this sum enumerator. First is a recurrence relation. This one is coming from the theory of Gantt polynomial, and so what we have is this double enumerator satisfies a quite clean recurrence relation. Other than this is a double summation, but other than the terms we want, other terms are just simply a polynomial or some Gaussian coefficients. Furthermore, using the lemma of Gassel and Vinot, we can obtain that when S is 1 over T, then this double enumerator actually give you Q analog of the Narayana numbers. This non-crossing lattice path view can also tell some other things kind of interesting. So this is another picture of this pair of non-crossing lattice paths. And when you look at the enumerator of sum of AI and the sum of BJ, then in picture, what you are counting is just actually the areas bound below by the first lattice path and the bound on the left but by the second lattice path. Another way to see this is kind of changing this picture into plane partition by filling the red, white, and the blue part by the integers 0, 1, 2. So this is a kind of special case of a plane partition. Well, what I'm interested in is how many zeros, how many twos are there in the plane partition. I didn't find a formula available, help me counting this. So I kind of take another point of view. So you're looking at this is right grid and looking at the columns. So it's clear the columns kind of from left to the right following some order. They are kind of items in certain poset. So pursuing from that direction, we find out, well, exactly those columns will form multi-chains in a special poset. And this is the picture of the poset. The 5 columns I have here from the right to left corresponding to this 5 right points in my poset picture. Oh, by the way, in my poset, 0, 0 is the minimum element. 2, 2, 2, 2 is the biggest element. So my order is 10 to the right. Interestingly, this poset actually is something show up exactly in Stanley's EC1. If you go into the chapter 3.5, which discuss multi-chains in distributive lattice, you see this example, and there are several interesting results. So I just listed them here. So this Narayana number giving me how many such things are there, also counting different things in the poset. But that's not what's kind of important for me. Important for me is on this poset, there is a kind of clear like deck path structure. So you can use the usual decomposition for deck path. So that's kind of give me this study that gave me a way to decompose this and obtain the recurrence to study this double enumerator. So what we have found that if we take a generating function, then it satisfies a Catalan form recurrence. Catalan form recurrence, meaning there's a kind of 2-degree recurrence in term of convolution. And from there, we can obtain the generating function is always the rational function, where the denominator is very neat. It's always a product of factors like this simple form. The whole expansion is kind of complicated and have a lot of terms, so I didn't write down here. To end my talk, the last thing I want to mention is kind of an interesting observation, and I would love to see if anybody have seen something and have encountered some similar phenomena. So what happens if in our enumerator, when you let S and T to be 1, so that's basically go back to counting how many PQ parking functions are there. What we got is this generating function, summing where the coefficients are Narayana numbers, is a rational fraction and is of special form. where the denominator is a power of 1 minus 3, but it's always odd power, and the numerator is nothing but the Narayana polynomial defined by this equation. It's starting from constant coefficients. So I think this is kind of pretty neat. And I did a quick check, but I didn't find it in any literature. But I think something like this must know. And I would really be interested if you can give me any reference or suggestions, especially what other combinatorics it corresponds to. So I guess that's all I want to say. And thank you for your attention.